Hello, so here is a nice question on real analysis. The question is, let's say f is a function from closed interval 0, 1 to r, which is differentiable, and it is given that there doesn't exist any x belong to closed interval 0, 1 such that f of x equal to f dash of x equal to 0. Then you have to prove that f can have finitely many zeros. That is, the number of zeros of f must be finite. So let's see the solution. So given that f is differentiable, which means that it is continuous on 0, 1. So we'll prove it using contradiction. We have to prove that f is finite. I mean, f has finitely many zeros. So we'll assume that, let's say, f has infinitely many zeros in the closed interval 0, 1. So let's say x1, x2, xn. These are infinitely many zeros of f. Now these xn's belong to closed interval 0, 1. Therefore, by Bolzano-Weierstrass theorem, there exists a subsequence of xn which converges to some alpha which belong to closed interval 0, 1, which implies that f of x and r converges to f of alpha, because f is continuous. We are just applying the definition of continuity, the sequential definition of continuity, which implies that f of alpha equal to 0, because f of x and r is 0, because x and r is a subsequence of xn. Yeah. Now, what is f dash of alpha? Now, f dash of alpha is basically this, the limit x approaches alpha, f of x minus f of alpha divided by x minus alpha. Now, here we will apply the sequential definition of derivative, which says that I'll just put x and r, which is sequence x and r, in place of x, and here I'll approach n approaches to infinity, so which is 0. So f dash of alpha is 0. That means that we got a point in 0, 1 where the functional value is 0 and the derivative is also 0, which is a contradiction, because we already assume that there doesn't exist any point in the closed interval 0, 1 whose functional value and the value of the derivative is simultaneously 0. This is not possible, but here we got a alpha when we assume that f has infinitely many zeros, which is a contradiction. Therefore f can have finitely many zeros, and we are done. Thank you.